Namaskar students. In this video, we will discuss about exponential distribution. Exponential distribution, it is a continuous probability distribution. So here we will be discussing its probability density function, its CDF cumulative distribution function, and with the help of its moment generating function, we will be finding its mean and variance. So we are assuming here a random variable x. This is a continuous random variable. This random variable x is said to have an exponential distribution. We have one parameter for the exponential distribution. That parameter we are taking here as lambda, and this parameter lambda is greater than 0. If its PDF probability density function is given by this function f. Here this f is defined as lambda times e raised to power minus lambda x when x is non-negative, and for negative values of x we have this function f as 0. So this is the probability density function. If the random variable x has an exponential distribution, the parameter which is involved here is lambda, and this parameter lambda is greater than 0. We can easily verify that this PDF, this given f, it will be satisfying the properties of probability density function. It is integrable, it is non-negative in nature, and when we will be integrating it within the limits minus infinity to infinity, with respect to x, we will be getting this result as 1. And very easily we can verify this result. If I consider here, if we verify this property of the probability density function here, so we have minus infinity to infinity, we have to integrate, but as per definition of this probability density function, these limits, they will reduce from minus infinity to infinity, they will be reduced to 0 to infinity, because only within this interval this function is non-zero, and the value which this function f is assuming, it is lambda e raised to power minus lambda x dx. And very easily we can integrate it. It is lambda, we will be having here in the denominator also, we will be having minus lambda when we'll be integrating, and we have to take here the limit from 0 to infinity. So when we'll be taking this limit, it will come as 1. So this verifies the property of probability density function, that if we are integrating our probability density function within the limits minus infinity to infinity, then we get always 1. Now, CDF of exponential distribution, it is given by this particular form. It can also be easily proved. What is the CDF? CDF is, if you're finding the CDF at x, then it is the probability that the random variable x is less than equal to x. And if we write it in the terms of the integral, then it will be this integral from minus infinity to this point, which is x. We will be integrating the probability density function here, whose notation is f here, with respect to x. And we will be considering here two cases depending on the definition of our PDF. We will be considering two cases when x is less than 0, and the other one will be when x is greater than equal to 0. And by integrating it very easily, we can verify this result that the CDF will be having this particular form. Now, next, we will be finding the moment generating function of the exponential distribution. So as we know that the moment generating function, this is the notation for the moment generating function. We are finding here the moment generating function of the random variable x, and it is the expectation of e raised to power tx. And when we will be finding the expectation of e raised to power tx in the case of exponential distribution, we will be getting it as lambda upon lambda minus t. Now, let us prove this result that the moment generating function will be given by this way. So here let us consider the moment generating function of this random variable x, which has an exponential distribution. So by the definition of moment generating function, it is the expectation of e raised to power tx. And since here the random variable x is a continuous random variable, so when we will be finding this expectation, we will be using here the integral. It will be given by this integral, which will be from minus infinity to infinity. Then we will be having e raised to power tx, and then we will be having our PDF in the product fx, and this will be integrated with respect to x. Now let us take here this PDF. Let us put here the probability density function, which we have here for the exponential distribution, which we have discussed just now. So when we will be putting here fx, as per definition of our probability density function, this fx, these limits, they will change now, they will reduce to 0 to infinity. And let us put here the probability density function, which is lambda e raised to the power minus lambda x, and we have to integrate it with respect to x. And it is very easy to integrate it. Lambda is constant. Let us take it outside. And we have the limits here from 0 to infinity. And we can, here we have e raised to power tx and e raised to power minus lambda x. So if we take here minus x common, then we will be left with lambda minus t x. Now let us integrate it. When we will be integrating it, we will be getting here minus lambda, lambda minus t, and we will be having here e raised to power minus time lambda minus t x, and here the limits are from 0 to infinity. So when we will be putting these limits, we will be getting here as lambda upon lambda minus t. So this is the moment generating function for the random variable x, which has exponential distribution. So we are able to prove that the moment generating function is here lambda upon lambda minus t. Now we have very good result that if we read the coefficient of t raised to power r upon r factorial in the moment generating function, then that coefficient is the rth moment about origin. Means what we are saying here, we have here result, we know that this is the rth moment about origin. The notation is bur dash for the rth moment about origin, which is given by expectation of x raised to power r, because this movement is about origin, rth movement about origin. And what is this? This is the coefficient of t raised to power r upon r factorial in movement generating function. This is the movement generating function of the random variable x. Now let us find out the first movement about the origin and the second movement about origin from this generating function, from this obtained generating function. So for finding the coefficient here, coefficient of t and coefficient of t square upon 2 factorial, we will be rewriting this moment generating function, which is lambda upon lambda minus t, in the form of series. And very easily we can write it in the form of series. So let us write it in the form of series here, as we have seen that the moment generating function, which is expectation of e raised to power tx, we are getting here as lambda upon lambda minus t. And we can further rewrite this as, if we take lambda common in the denominator, we'll be having here this one. So this is 1 minus t upon lambda raised to power minus 1. And if we write down its series, then the series will be 1 plus t upon lambda, then we will be having t square upon lambda square, t cube upon lambda cube, and so on. Now, if we read here mu1 dash and mu2 dash, the first not central movement, the first movement about origin, mu1 dash. So mu1 dash is the coefficient of t in this movement generating function. Coefficient of t in movement generating function. And if we see this series which we have for the movement generating function, here the coefficient of t, we have here in this term we have t, and if we check the coefficient of t, it is 1 upon lambda. So here the first movement about origin is coming as 1 upon lambda. Now for second movement about origin, we will be finding the coefficient of t square upon 2 factorial. So we have t square here, but we don't have 2 factorial. So what we can do, we can multiply it with 2 factorial and we can divide it by 2 factorial. Now if we check here, the coefficient of t square upon 2 factorial, then that coefficient is now 2 upon lambda square. So if you write down here mu2 dash, which is the second movement about origin, and it is the coefficient of t square upon 2 factorial in movement generating function, then from this series we can see that this coefficient of t square upon 2 factorial, it is 2 upon lambda square. So we have first two movements about origin. Now, if we find out the mean, we know that mean is the expected value. Mean is the expected value, and it is equal to first movement about origin. And we have just seen, we can see here also that this mu1 dash is the coefficient of t in movement generating function, and here this coefficient of t in the movement generating function is 1 upon lambda. So here from this movement generating function, we are finding the mean, and we are able to verify that the mean in the case of exponential distribution is 1 upon lambda. Now for variance, we know that variance, which is sigma square, this is the second central movement. Now we are talking about central movement, the movement which is about mean. So the second central movement gives us variance. And we know that mu2 can be written as mu2 dash, where mu2 dash is the second movement about origin, minus square of mu1 dash. So this implies this variance, which is mu2. Let us put here mu2 dash. Mu2 dash, we have evaluated mu2 dash is the coefficient of t square upon 2 factorial in movement generating function, which is 2 upon lambda square. Which is 2 upon lambda square, and mu1 dash is 1 upon lambda. We need it square, so it is 1 upon lambda square. And if we simplify it, we are getting it as 1 upon lambda square. And in this way, we are able to verify here that the variance in the case of exponential distribution, it is 1 upon lambda square. The mean is 1 upon lambda, and the variance is here 1 upon lambda square. Now, how mean and variance, what will be the relation between mean and variance, which will be greater and which will be less? It depends on the value of this parameter lambda. So we have two cases here, as we know that the parameter lambda is greater than 0. So the first case which we are considering is when this lambda is less than 1. So if lambda is less than 1, then if we compare lambda and lambda square, then lambda will always be greater than lambda square. And if we take the reciprocal, then this inequality, it will change and we will be having this one. And what is 1 upon lambda? 1 upon lambda is the mean of exponential distribution. So for this particular case, we will be getting here that mean is less than variance. Now, if we come to the second case, in second case, let us consider that this lambda is greater than equal to 1. We are considering here lambda greater than 1. Because see, if lambda is equal to 1, then both mean and variance, they will be equal. Now, if lambda is greater than 1, then in this case, if we compare lambda and its square, lambda square, then it is clear that lambda square will be greater than lambda. And if we take the reciprocal, then the inequality will change. Then 1 upon lambda will be greater than 1 upon lambda square. And this implies 1 upon lambda is the mean of exponential distribution, that the mean is greater than variance. So in this way, we have evaluated the mean and variance of exponential distribution with the help of its moment generating function, which is lambda upon lambda minus t. Thank you. Have a nice day.